All right, everybody, here we are. Final segment for the day. Remember, our goal was to figure out the KEQ for the reaction of the ammonium ion with chloride to make the HCl with the methylamine to make ammonium ion and chloride. It's a couple pages back in the notes. And just in summary, the acids were, well, wait a minute. Those weren't my acids there. Acetic acid came up later. And HCl is the acid up there. HCl is one of the acids up here, and its conjugate base is on the top. And here, methylammonium is the acid right here, and its conjugate base is in the bottom. So we're going to have to learn these pKa's. I just copied a page straight from the textbook. We have to learn them to use them as if they're as important as electronegativities for atoms. So we don't want to be looking those up every time we need to think about polarity of bonds. So we don't want to be looking these up every time we want to think about how strong an acid is. Next day, we'll talk about why these are the weakest up at the top and the strongest on the bottom. And what the P is, we already know. It's the negative log of Ka. Px is always the negative log of x. So if we take the if the negative log of the pKa is 50, then the Ka itself was 10 to the negative 50. Sorry, I got something in my throat. Okay. And right now we're just going to use these numbers, and we need them. So we have HCl at the very bottom. It's in this list here. And we're going to learn its pKa is -5. And the methylammonium, we got to figure out which entry on the table it is. So pKa here. Now there's 2 nitrogens on there. Please don't pick the wrong one. It is not this nitrogen here that's neutral, losing an H. It is the nitrogen with a positive charge losing an H. It's this one. These R's can be carbons or hydrogens or combinations thereof. So the number we need here is 10. Weak acids have positive pKa's. Strong acids like HCl have negative pKa's. It's because the Ka is large to get a negative there. Ka, if we're using this number to be exact, would be 10 to the positive 5. What do you get when you do the negative log of 10 to the 5th, which is Ka? You get this. What do you get when you do the negative log of 10 to the negative 10? You get that. So that's very small for an equilibrium constant. That means not very reactive. This is very big for an equilibrium constant. It means this is very reactive. That's a preview. We'll talk about acid strength Monday next. So all I'm going to do is write down the Ka reactions for these two. HCl Ka reaction. And it's good to review. And we need CH3 NH3 plus Ka reaction. Short form for reaction, I like to use RXN. And HCl will react with what molecule in the Ka reaction? Water. What do you make in all Ka reactions? Everyone? Every single one is what I should have said. Hydronium. So both of these will have water reacting to make hydronium. And in this one we have CH3 NH3 plus reacting. and it will create CH3NH2. Keep in mind your goal has both of these red species in this reaction and in this reaction. So Ka for the first one. You're gonna get a straight plus with that, but that's fine. See if I can move it. I think they're linked. Yeah. So Ka, the reaction, they're linked. Wonderful. There. Ka is defined as products over reactants keep water out. H3O plus. These are already in our notes, over HCl with Cl minus on top. And Ka for the bottom one, H3O plus times CH3NH2, products over reactants for every equilibrium constant ever over CH3NH3 plus. I have one simple question for you. Keep your goal in mind. The only question is does this thing have my red variables in the correct spots to be matched with two of the variables up here, or do we have to flip it? And in the first Ka, everything is where I need it. Cl minus on the top, Cl minus on the top, HCl on the bottom, HCl on the bottom. In this one here, it seems like a flip is necessary. So I need, I'm gonna call this Ka1 and this Ka2. So Ka1 Ka2, but I need to flip it. Oh. One over Ka2. Now my dot's not in a good spot. Sorry, I'm starting to hurry a little. I don't know why. Ka1 times 1 over Ka2 gives us Keq. That's good. I know Ka1 and I know Ka2. Ka1 is this one, and Ka2 is pK is 10. I didn't write it down. Right there's 10 to the negative 10 is Ka2. So I'm going to take Ka1, 10 to the 5th, and divide it by 10 to the negative 10, and I get 10 to the 15. Wow. And if you remember the reaction that went with this, which I forgot to bring over, the whole goal was to figure out which way that reaction was going. So I should have grabbed the reaction too. It's 3 pages back, I'm pretty sure. No, there's our goal, and the reaction's right above it. Cross fingers. I'm going to get some titles. It should do it. I want to know why I drew one arrow bigger than the other in the equilibrium. Yeah. Here's the equilibrium. Why did I draw the top arrow bigger than the bottom arrow? Well, now we know why. We got a Ka of 10 to the 15th, which means you have 10 to the 15th times more products than reactants. So that bottom arrow is actually a huge exaggeration. It should be almost invisible, smaller than a dot, because the top arrow is 10 to the 15 times more. And we got that all from Kas, didn't we? Okay. But these numbers are, they get to be vast, either very, very large or incredibly, incredibly small. And it's hard to talk about that. If I had to have words for the number 10 to the 15th, I'd have to say, let's see, a trillion is 10 to the 12th. I need 10 to the 3 is 1,000. This is 1,000 trillion. Wouldn't it be a lot easier to say pKeq is negative 15? Isn't that a lot easier to say? Isn't that why all these are P's instead of K's? For instance, the Ka for an alkane is 50. The pKa, sorry. That means the Ka was 10 to the negative 50. I don't even have words for that. Let's see, 10 to the negative 12 is a trillionth. And then it's a trillionth of a trillionth of a trillionth of a trillionth, gets you to 10 to the negative 48. Then it's a hundredth of that. Do we like saying that? Ka is a hundredth of a trillionth of a trillionth of a trillionth of a trillionth? Or would you rather say pKa is 50? I think I know your answer. Similarly down here, we like to say, although the numbers aren't too unreasonable, instead of Ka is 100,000 for these 7 strong acids I have here, we can say pKa is negative 5. It just makes talking about these things a lot easier. And the summary, I'm going to steal from the book, and it's the gospel truth, and we use pKs to get to the answer. And summary here first. pKeq negative 15. The negative log of 10 to the 15th is negative 15 because the log of 10 to the 15 is 15. Multiplied by negative 1, you get negative 15. Negative pKs means reactions go to the right. That's products. Positive pKs means the reactions stay to the left. They favor reactants. It's just like strong acids make a lot of hydronium. Okay, and they have negative pKs. And weak acids make very little hydronium, and they have positive P's. Positive pKa means weak. Negative pKa means strong. I want to grab from the textbook something off screen, and it'll appear miraculously. I think I got to go back a few pages from where I was. There you go. It's in a square box. There's a lot of algebraic determinations in the textbook. You don't have to do any of them. You just have to believe what's in the shadow boxes. I'm going to grab one right now. Hopefully it comes pretty clear. And there's one right here. And I'm going to put it down here. So if you want to predict pKeq for any reaction involving 2 conjugate acid-base pairs, I'm going to write that down. For any reaction between 2 conjugate acid-base pairs. For any reaction between 2 conjugate acid-base pairs. You can use this equation with certainty that it is true. The math derivations of it were in the book, and you will never have to do those. And here we are. Okay. You take the pKa of the reactant acid, and the way we do things in this country, we go from left to right. Reactant acid is left side of the equilibrium. side of equilib. And the product acid is the one on the right. So we looked up, here's the easy way to get to the answers in this problem. We looked up in this equilibrium, this, and we found it to be 10. And well, we're not going to look it up on the test. It's going to be in our head. The 10 is on the right, and the -5 was on the left. -5 minus 10, no surprise, -15. Look at that. We did a lot of work to get there here, didn't we? We didn't have to do a lot of work because inside our heads is the pKa's, and therefore KEq, this is pKeq. You take 10, it's called an anti-negative log. The negative, oops, let's put that outside the parentheses. We're almost out of time. The negative of -15. This is not hard, is it? And no surprise there, KEq, which we did a lot of work to get to 10 to the 15th. This is a lot easier work, isn't it? So take home message for the weekend. Get the pKa's into your head, learn them, keep them beside your bed, review them every night. They'll eventually start sticking. And I want to confess, a lot of them are rounded. Notice the numbers are often very nice, 0s and 5s. These I couldn't lie about because we have to know alcohols are a little less acidic than water. And these are a little more specific. And this I really took some liberties with. Some of them go up to -9. Perchloric acid's closer to -9, and so is HI, and so sulfuric acid. A lot of them are closer to these numbers, but the confession is revealed here. They've been rounded ±4. That way you don't have 7 numbers to memorize. You're welcome. And that brings to a conclusion today's lecture on pKa and acid spaces, etc. We'll pick it up again on Monday. And until then, I bid you adieu.